Hello everyone. Today let's learn about a simple and interesting topic, that is BCD to ASCII conversion. So let's know about the BCD and ASCII. BCD stands for binary coded decimal, whereas ASCII stands for American Standard Code for Information Interchange. The binary representation of 0 to 9 is called BCD. In computer literature, we come across two terms for BCD numbers. The first one is Unpacked Bcd and the second one is Packed Bcd. So the first one is Unpacked Bcd. In Unpacked Bcd, the lower 4 bits of numbers represent BCD number and the rest of the bits are 0. Consider this example 00000100. This is an unpacked BCD for 4. Similarly, the other digits from 0 to 9 are also represented as shown beside. Here, the unpacked BCD takes 1 byte of memory location or a register of 8 bits to contain the number. So let's go to the second one, that is packed BCD. In packed BCD, a single byte has 2 BCD numbers. Here, one BCD number is in the lower 4 bits and one in the upper 4 bits. For example, consider 0110-0100. This is packed BCD for 64. Here, it takes only 1 byte of memory to store the packed BCD operands. The advantage of packed upon unpacked BCD is that it is twice as efficient in storing data. In ASCII keyboards, when key 0 is activated, 30H, as we know, is represented by 0110000 is provided to the computer. Similarly, 31H is provided for key 1 and so on, as shown in the above table. Search for a clue in the table to find ASCII value for each unpacked BCD number. Let's move to the next topic, that is packed BCD to ASCII. From the previous table, we can observe that by adding 30 to the BCD digits, we can obtain the ASCII character. This was the clue I was telling to search for. Let us take an example. Consider a packed BCD number 24H. The packed BCD number 24H is converted to unpacked BCD numbers 02 and 04, which is then added with 30. So, the ASCII value for 24H are 32H and 34H. Have you ever wondered how the packed BCD is converted to unpacked BCD? Let's take a look at the truth table of AND gate. So, by seeing the truth table, we can say that if any one of the inputs is 1, then the output will be the same as the other input. So, ANDing 1, 1, 1, 1, that is F, we get the same digit. Let's take the example which was shown before, that is 24H. If 2 and F are ANDed, we get 2 as the result. Similarly, if 4 and F are ANDed, we get 4 as the result. Keeping that in point, we can now convert the packed BCD into unpacked BCD by ANDing the digits with 11110000, that is nothing but F0H, and 00001111, that is nothing but 0FH. Now ANDing the number 24H with F0 and 0F. This method is also called masking. 24 ANDed with F0. By expanding it, we can see that we are just ANDing the higher nibble, so the output is 20H. Similarly, 24 is ANDed with 0F. By expanding it, we can see that we are just ANDing the lower nibble, so the output is 04H. We got 20, but we need 02, so we have to shift towards right 4 times. Now we obtain 02H. Whereas 04 is in the correct order. After shifting, we add 30H to both the results. Therefore, the ASCII digits are 32H and 34H.
So now let's see the practical approach by executing the program. First, we have to mount the specific file in C drive, which is named as MP. So mount space C colon \MP. Now we have to enter into C drive. So C colon. To open a new file, we have to type edit space file name. Here I am giving the file name as bcd2 ascii.asm. I have already written the program, so let's go through the program. First line, dot model small tells that our program is small. In the second line, dot stack defines 64 kilobytes of memory to the stack. Dot data means start of data segment. Next, BCD space defined byte space 48H. In this, we are storing the value 48H into the defined byte BCD. ASCII is defined byte which stores the answer. DUP reserves primary location. Dot code starts the code segment. Now MOV space AX, at data. Here we are moving the data location into AX. Next, MOV space DS, AX. Here we are storing the contents of AX to DS. The next line, MOV space DL, BCD. Here we are storing the value of BCD into the register DL. Now in this line, AND space DL, 0F0H. The value of DL and 0F0 is ANDed. Theoretically, it should be F0, but actually, if any letter is added at the start of some value, it won't identify the value. So we put 0 at the start to make the value to be read by the register correctly. The next line, MOV space CL, 4, where we are storing the value 4 to CL, that is count register. The next line, SHR space DL, CL. Shift towards right. CL is 4, so we are shifting 4 bits to right. Arithmetic instruction add space DL, 30H. We are adding the value of DL with 30H and the sum is stored in DL. MOV space ASCII, DL. Here the content in the register DL are copied to ASCII. Contents of BCD are copied to register DL. And space DL, 0FH. Now to take the lower nibble, we AND DL with 0FH. The value is stored in DL. Now 30H is added to DL. The value is then stored in ASCII +1. Then the program ends. Now let's save the file and exit. Now the next command which we have to type is masm space file name, that is bcd2 ascii dot asm semicolon. So we can see that there are no errors. If any errors occur, then go back to the first step. Now the third command is link space file name, that is bcd to ascii dot obj semicolon. Now we have to debug the exe file of bcd to ASCII. So the command is debug space bcd to ascii dot exe, enter. Now we have to type capital U, that is nothing but unassembled command. So we got the start offset address. Now we have to find the end offset address. So type U again. So at 0025 we can see that we got MOV AH, 4C. So we have to type G equals the start offset address is 0000 space the offset address of AH, 4C is 0025. Now we have to type D space DS colon 0. We can see that the answer lies in the first line at the end. Here is the mark. Now to quit, you have to press Q and then exit. Thank you.